Hello, I'm Ceren, and I work as telecommunication design engineer at Planes. And today I will talk about our high-speed receiver and details about it. So first, I will briefly explain what we do, how we do it, and our satellite communication links. Then I will go towards the more detailed one, from generalized links to high-speed link to high-speed downlink, and my receiver algorithm and sub-blocks of it, and so on. So for starters, Planes Satellite and Space is a Turkish company. We have built 3 years ago. We were founded 3 years ago, and within 3 years, we have successfully sent 9 satellites to LEO orbit. 5 of them were actually test satellites, and we sent them just to flex on our capabilities, learn how to do satellites. The ones at the bottom are our test satellites, and the ones that on the upper corner are the 4 IoT satellites. Gizem will talk more about what we do with those IoT satellites. We are sending our satellites using SpaceX Falcon 9 missions, Falcon 9 rockets. And we have 3 ground stations that we have built ourselves, 2 of which are situated in Ankara, Middle Anatolia, and 1 of them is situated in Erzurum. This is actually a picture of our ground station in our headquarters. All of our ground stations are GNU Radio based, and we use USRPs with that. Also, we have various agreements with different ground station service providers, and they are GNU Radio based as well. So I work extensively with GNU Radio. We do also have SatNOX stations. We cooperate with them, so you can use our SatNOX stations to get a plan for a listening session for whatever satellite that you are interested in. I have a video here. It summarizes what we have done so far quite well. So I would like to play that. This one. For next up, we have, as you have seen in the video, we have IoT satellite. So I will give you a brief explanation of how we start communicating with the satellite. I couldn't, yes. First off, once the integration is done, we send our satellite to Germany, actually. We work with Launch, and they perform integration with the deployment pod. So they sent that satellite after integration, they send it to SpaceX to America, and after that we wait for the launch date. And during launch date, we do the following. We first wait in our mission control room and to hear separation confirmed. And usually, well, luckily, our most recent travels were done around Turkey, on top of Turkey. So we have satellite comes to us very soon after the separation is confirmed. I have another video for that. Yes.
3, 2, 1, ignition. And liftoff Falcon 9, go Transporter 11. Connecta IoT 1 deploy confirmed. Connecta IoT 4 deploy confirmed. Connecta IoT 2 deploy confirmed. Connecta IoT 3 deploy confirmed.
Once the deployment is confirmed, as you can see here, this was actually the live, this snippet is actually taken from live recording, live broadcast on YouTube. We were here, and once the separation is confirmed, we wait for satellite to come exactly what elevation we need, and then we attempt to communicate with it. So, why is it very important to communicate with the satellite is because first, if you can establish a successful communication, it means that it's alive, it's working properly. Second, we want to get vital information as soon as possible so that we can intervene with it as soon as possible. And also, if you establish a communication, it means that you have found your satellite. This is actually, it's been going quite well. We have established communication just 7 minutes after connected T2.1 separation and 3 minutes after T.1 and T.3 separation. On the right side, you can see us in the ground station right after T.1 successful communication. Also, you can watch this live video over the internet. I added the link to watch it. It's entirely in Turkish. However, you can see how we react here once the separation is confirmed, how we are working together with, you see the GNU Radio flows here, and it's very exciting in general. So speaking of which, about the spectrums, we pre-plan some SatNOX stations and we tune them for our satellite. I've added the link for Connecta IoT1 observations. You can just write Connecta and all of our satellites will show on the SatNOX. And you can actually see the waterfall of it. There's actually an audio file. Well, it's not actually audio, but if you want to listen to the spectrum, you can as well. And also here says data section. And in that data section, SatNOX ground stations use GNU Radio as well, and they decode our actual telemetry data and show you in a screen like this what's written in there. So we usually put vital information about the satellite there, but we sometimes put fun things to write. For example, this is from 29th October. It was the birthday of Turkish Republic. So it says, Cumhuriyetimiz 100 yaşında. It literally says our republic is 100 years old. Speaking of which, in Turkey, we have 25 satellites, operational and functional satellites right now, 9 of which that plan has sent. So this is very few. It's not bad, but it's few. What we want to do is we want to increase it. How do we increase it? We want universities to send more CubeSats. We want private ventures to send more CubeSats. And we want everyone actually to contribute to the space science. That's why it's important to have such organizations, especially open source environment organizations. Let me talk a little bit about our communication links. We have 6 links in total. UHF link is the main lifeline of a satellite. You send commands there, you get vital information from there. High-speed link is, well, it's vital too. You can send software updates and you can download images, videos, huge chunks of IoT data. We've actually tested our RF, it's not optical ISL, it's RF ISL link to transfer IoT data from one satellite to another so that, let's say, the first satellite A has a data that I'm interested in, but it's not in my line of sight. So what I do is I schedule a command, it sends to another satellite, but and the second satellite is in my line of sight, so it sends to me back. We have direct-to-satellite link and gateway-to-satellite link. These are all IoT links, and Gizem will be talking about them. And next, we have an expand downlink, which is still in progress, still in being development, and we will be using it for Earth observation purposes. So in order to hype you up about communication links, these are the examples of what we have done using our high-speed link so far. Those 3 images are taken with a camera, downloaded with our high-speed downlink. These 2 videos, actually this one is very nice. Since they were test satellites, we did... Okay, that's...
Freundschaft ist eine lange Reise. Es gibt süße Zeiten und Zeiten, in denen es rund läuft. Wir sind da.
Okay, German advertisement. Since we have sent so many test satellites, we did kind of crazy stuff with them. Actually connected 1.2 has a selfie stick. So you will see the video of it. As you can see, it's very spooky, like there's no one there. Is there anyone there? It always amazes me, space. And now we have another 4K video shot from space. Do we have any? Yeah, no. Actually, I need to adjust this. Yeah, okay. Why is this not playing? This shows Mediterranean Sea and Black Sea. I don't know why this is lagging, but the original video isn't. It shouldn't be. You can see the sun here. I think that's Cyprus. Is it? Yeah. There are way more videos in our YouTube channel. You can check them if you'd like. So let's get started. So how did we download all of the information that all of the videos that I've sent? We are operating in full duplex. We are operating at S-band, which is between 2 and 2.5 gigahertz. Our payload, which is the thing that you put into your satellite to communicate with the ground station, is our own design. And in the ground station, we have GNU Radio plus SDR. For waveform, we always use international standards to be able to work with different international organizations, and the most prominent one is CCSDS, as you know, and its features are as follows. We do have a scrambler, we do have concatenated convolutional code, which is Reed-Solomon plus convolutional code with different puncturing rates, and we do have a QPSK modulation. So in the link, I have actually made a MATLAB simulation using ground station properties, antenna properties, RF properties of the transceiver payload, and our actual satellite TLE data. And turns out that our dynamic range is in between minus 101 dBm and minus 83 dBm. As you can see here in the... Is this working? Yes, this is working. Here you see the Doppler, expected Doppler shift curves in here. It's different for the dashed line is for uplink, the other line is for downlink. So as you can see, maximum Doppler shift that I will be getting is between plus and minus 50 kilohertz. Moreover, we can define Doppler rate as the rate of change is the change in unit time in Doppler frequency. So as we approach to 90 degrees, so the satellite is passing from your top, Doppler rate increases because the speed, the frequency changes very rapidly. So we have maximum of 777 hertz per second of Doppler rate, which our receiver should be able to recover from. Also for that data rates, it ranges from 125 kilobaud to 4 megabaud. As I said, it's high-speed link, but I've put some very low speed, like 125K, just in case, so that if everything fails, maybe something happens with this antenna, some operational problems happen, so that we can still communicate with it. Also, we will be doing continuous transmission, so that when the satellite is sending data, it just sends data, and when it's not, it just keeps sending idle gibberish frames. So here is my design. As you can see, there are lots of different blocks here. The white and black ones are generic GNU radio blocks, like USRP source automatic gain controller, and so on. The red ones are my additions or my modifications. These phase stepper and node synchronizer, they are borrowed from SATLab's GNU Radio OT module. And in the bottom, you see a container. It actually shows up like this in the GNU Radio flow graphs, so that when operation team uses it, when test team uses it, it looks nice and easy to navigate around. I will go down one by one and explain you main reasons why we did it, what we did. So first off, we're working with QPSK modulation. And the biggest problem is, well, one of the biggest problems is phase ambiguity. Here you can see my symbols there in 4 quadrants, but my receiver, my symbol synchronizer, here, Gardner symbol sync, cannot possibly know where my first set of symbols start, at which phase my symbols will start. So it can, if you imagine, it can be started at 45 degrees and it looks like this. It can be starting at 135 degrees, so it will be shifted 90 degrees. It can start the other one, another shift, other one, another shift. So I have 4 different probabilities for where my symbols should be located at. In order to combat that, we can use differential encoder, which is NRZM encoding. And what that does is that instead of modulating bits, it modulates, well, it first maps bits into bit transitions. So therefore, you get a 180-degree symmetry over the y-axis, no, x-axis. That's okay, but we still have 90 degrees of phase ambiguity. So they would be looking like this or just 90-degree shifted version of it. In order to check for it, receiver should be multiplying it by 1, like at the 0-degree phase, and with 1J at 90-degree phase, and check which one is correct. How do we check it? We check it by syncing to our header. At the output of the frame sync here. I've got some possible solutions for it, like it's straightforward, right? Logic says it multiplied with 1, check one branch, multiply it 1J, check the other branch. However, this does not work in GNU Radio 3.0. I'm assuming because of the buffering system, first branch and the second branch, they are operating at different data rates in practice. For example, if I have a sync here, inputs are consumed and outputs are generated here, but then nothing happens here, and vice versa. So therefore, buffer here cannot know how many outputs to consume, how many outputs to push to either of the branches. Therefore, we lose frame count. Another possible solution is that I've attacked the buffer directly. So, okay, buffering doesn't work, so I will open up a FIFO. 2 separate FIFOs, and I have 2 separate flows in the below. So here, I generate my samples. This goes to here and here. They are duplicated. They are sent in a buffer and separate, 2 separate buffers. And 2 of these flows are actually working separate from each other, independent from each other. Although this solution works perfectly, I have no frame counts, I have no sensitivity losses, so on. However, this is not a good solution. Because imagine if you remember the ground station that I've showed you, if I put 3 different flows to 9 satellites for just only 1 link, well, it's not a good system. So what I did is I opted out for a SATLab solution, and here, yes, here, as you can see, it multiplies phase stepper, does the multiplication of phase shift, and it's directly linked to my frame synchronizer. So if the phase is okay, if there's a synchronization, it says, okay, phase, you found the correct phase. If not, however, our samples kind of start to pile-up. I'm not sure if that's the correct word to describe it, but we need some sort of corrector block to ensure every sample is being treated by every one of these blocks. So what it does is that if there's a sync, nothing. If there is no synchronization, it just slows down the production of samples at the output. Also, with that we can resolve phase ambiguity problem. Now I will move on to Doppler compensation here. So in order to avoid some costs, actually both at the uplink and downlink, we do Doppler compensation using this piece of code. It's actually developed in Python. What it does is that it makes use of this satellite tracker library, and it reads TLE data. TLE data is like two-line element data, and it kind of computes radial velocity. So using that radial velocity, you can easily calculate the Doppler shift that your satellite is under to, that your satellite is subjected to. So I calculated here, and I probed those values, and I just put it to my channelizer FIR filter just to correct for it. That's tackled too. Another issue we have is that, well, the symbol synchronizer block is specifically geared for high speed. What it means that it requires lots of samples to correctly operate. However, when I go for like 125 kilowatts, well, it does start working a little slow. So what I did is basically I made the resampling ratio a managed parameter. So if it's less than certain, if the baud rate is less than some certain point, output sample rate is increased. Another problem that we like to tackle here is that, as I said, my communication channel is a continuous channel. So USRP source is always getting some frames. I'm getting always some output here. So if I keep counting my idles, or if I push those idles to mission control software, everything fails. So what we did is, we're actually making use of space data link protocol in the upper layer, and we divided idle channels we've assigned idle channels to a particular virtual channel, and data frames to another virtual channel. So I get rid of them by checking the virtual channel. Also, it's a simple block, it's a PDU counter. The more PDUs come in, it just increments it. However, it will be relevant later. So here is my test schematic. I have one RF shield box here. This line you're seeing is RF line. Those below, those downward arrows are my control lines. So in RF line, I have my transmitter. It outputs 32, 33 dBm, quite high. I have various attenuations, and I have a variable attenuation, and I have measurement here. So I control this variable attenuation to see at which point I will get 1% of packet error rate. I also control USRP using GNU Radio, and my computer, I also control the transmitter like that as well. And the computer I've used is a pretty standard laptop that we have. And on the left here are the results. So for 4 mega baud rate, I have achieved minus 101 dBm of sensitivity level. And if you calculate what is supposed to be using minus 174 plus 10 log baud rate plus noise figure plus implementation loss and minimum SNR, it's actually pretty close to the theoretical value. On the right side, you have see the end result of all of this work. It's actually taken a few days ago. It's a real satellite pass. It's one of our Connecta IoT 1 satellites, Connecta IoT satellites. You can see the signal coming in here. We have some different probes for operational purposes. You can see the elevation degree here. It's at, 30-something degrees. You can see the constellation here. It's pretty nice, actually. And I have my counter here. So, about high sample rates. Well, as I said, I've even added a simple PDU counter because if you're using Python, well, high speeds won't gonna happen. It's just working way too slowly. Actually, for this setup, I used to have a PDU counter in Python, and it was giving me overruns. So when I changed it, it worked perfectly fine. Also, I've spent quite a lot of time. I have wasted quite a lot of time using SDRs connected with USBs. They claim to be able to reach that amount of sampling rate. However, USB 3.0, it's just like a natural bottleneck because like there are lots of USB ports on your computer, so they are sharing that resource. Also, your design, of course, should be compact and blah, blah. And another important point is that there is a debug file. There is actually a configuration file of GNU Radio, and here says the debug level. It's by default debug. It should be emergency, because when it's debug, it produces random informational output, and it prints out to your console. It says, for example, CRC OK, CRC OK, CRC OK, CRC OK. I have 1,000 frames per second, so it slows down. If everything fails, just use no GUI. And in conclusion, yes, we have talked about them. Tests verified that the receiver works at 4 megabaud. I have also didn't include it. However, I have tested for TLE error as well. So here we have this Doppler graph, Doppler frequency graph. I calculate my Doppler frequency using TLE data. But what happens if my TLE data is wrong? Especially during commissioning phase, it's usually wrong. What happens is that my Doppler curve changes a little bit around this center point, but the Doppler rate changes a lot more. So I have both a Doppler rate error and shift error, and I've used GNU Radio to simulate for that. I didn't include the outputs, but well, it was able to work with 10 kilometers, plus minus 10 kilometers TLE error, which is quite high. We never get that. This design works on different laptops. It works on ground stations. It works perfectly. So I would like to talk more about how I use GNU Radio in satellite communication, because I use it daily. I use it extensively. I use it for payload mockup, for instance, for starters. We were actually buying, that's funny, we wanted to buy a professional grade modem, and they had the receiver and transmitter structured in 2 very different waveforms. I asked them, okay, can we make it symmetric? Like, can I just use my receiver as a transmitter? And they looked at me dead in the eye. The reason why I want to mock up my payload is that I want to recreate my payload is that we're a small company and we are working very fast. Normally it takes years and years and years to build a satellite, to build a payload and send it to space and blah, blah, blah. But we're doing it in the order of few months. So I do support developers in that sense. SDR is a verified equipment. GNU Radio, I know it works perfectly well. For example, I measure QPSK output EVM of my waveform, and I go to the digital designer and say, oh, your EVM is, worse like 3%. So we use for that. Also, we use it for bit level operations and check if they are sending me more bits, because they always do, and it causes some problems in forward direct correction. I use it for channel modeling. As I said, I have kind of simulated. You know how expensive Doppler simulators are? Well, it shouldn't be, because we can use STR. As I said, I simulated Doppler error. I can simulate real Doppler case. I can simulate my amplitude variation. And I also even simulate LEO is a very crowded place, so we have lots of interferences. I actually mock them as well and see how my receiver reacts to it. Also, Another great thing about GNU Radio is that when things go wrong, in emergency cases, I just close the GUI, open the flow, change something, move on. So in a satellite pass, you usually have around 7 minutes, 10 minutes. So if I used something like professional grade modem, something like that, it wouldn't be the case. I wouldn't be able to recover from an error. I have put some thoughts in here. Well, pros of using GNU Radio is obvious. It's fast, you can use it for fast prototyping, testing, and it's ready to use. You can just give it them to people. It's cheaper, design is flexible. So when you buy a professional grade modem, your design kinda gets fixed. However, in Plan S, we would like to do interesting things, so we sometimes change our waveform. It's open source, so everyone's creativity gets to be involved in my design, like, where's he, Danny Lestevas? Hi. And let's talk about the bad things. Well, the actually huge problem I have here is in the last. There is no inherent mechanism to perform a version check. For example, when I open my flow graph and I accidentally disable a block, I wouldn't know unless it gives me an error. Sometimes, well, more often than not, it doesn't produce an error. I just disable something important. I change something important by accident. And there is no inherent mechanism to do the version check. And believe me, I've tried everything. I've tried naming it. I've tried comparing Python files. And when you consider 3 ground stations, lots of test laptops, personal laptops, different teams, operation team, test team, integration team, telecom team, blah, blah, blah. It's just a mess to do the version check. Also, related to that, cross-platform compatibility is a huge issue. Someone is using Debian something blah, something dot blah, blah, and someone else is using Linux 22, someone else is using 24. We actually froze some disk images. We have some disk images that is like, we found an optimal version of Python, UHD, GNU Radio, Linux, and so on, and we took the disk image of it, but that's not a good solution as well. And also, when I develop some OOT modules, like, I have to rebuild it every time I make a tiny little change, and I do lots of changes. So thank you for listening, and I would like to say it was a great journey to be here. Let's keep in touch. If you have any further inquiries, whenever you want to ask something, you can freely send me an email. Thanks. Bye.